You walk into a dark room, reach out, and flip a switch. Instantly, the room fills with light. It happens so fast, we rarely think about the journey that power took to arrive. But if we follow that copper wire behind the plaster, it leads out of your house, down the street, and eventually connects to a massive national control room. Here, engineers watch the entire country's power usage tick up and down second by second. They are doing this because of a strict rule of physics. Electricity, as it flows through these wires, is incredibly difficult to box up and save for later. Whatever amount of power is being generated right now has to be used right now. By flipping that switch, you join a network that spans the entire country, a system that has to adjust its total output in that exact same millisecond to keep the supply and demand in a perfect constant balance. To move all that power across the country, we use the national grid. Think of it like a vast transport network. The giant transmission lines you see cutting across the countryside are the high-speed motorways of this system, built to carry electricity over massive distances. Before the power can get on the motorway, it has to pass through a piece of equipment called a step-up transformer. This machine takes the raw energy from a power station and changes its shape. It pushes the electrical pressure, or voltage, way up, which mathematically forces the volume of flowing electrons, the current, to drop. This is a crucial trick. A lower current means fewer electrons bumping into each other. Fewer bumps mean less friction, and less friction means we don't lose our valuable energy as wasted heat while it travels hundreds of miles. Of course, that super high pressure is far too intense for your television or toaster. So when the power reaches your town, it takes an off-ramp into a step-down transformer. This reverses the process, dropping the voltage back down to safe levels before splitting it off into neighborhood streets and, eventually, your house. Without transformers carefully adjusting these levels up for travel and down for safety, a national power network simply wouldn't work. All the energy would burn off as heat before it ever reached your neighborhood. This animated line graph charts how our country uses electricity over a typical 24-hour period. We are creatures of habit. Every morning around 7 a.m., millions of kettles and showers turn on, creating a massive spike in demand. Then, around 6 p.m., people come home, turn on ovens and televisions, and we create another huge peak. To feed those huge spikes, we increasingly rely on clean energy sources, like giant wind turbines out at sea and fields of solar panels catching the sun. But nature has its own schedule. These sources are what we call intermittent. They only produce power when the wind blows or the sun shines. If we overlay their generation onto our daily routine chart, look what happens. The sun is strongest at noon, right when we are away at work or school, and drops off entirely right before our massive evening spike. The time we produce our cleanest energy rarely lines up with the time we actually want to use it, creating a headache for grid operators. To keep the lights on when the weather isn't cooperating, the grid relies on heavy lifters. Nuclear power plants provide our baseload, a massive, continuous foundation of energy that hums along day and night, rain or shine. Inside these plants, engineers use a process called nuclear fission. They take large, heavy atoms, like uranium, and carefully split them apart. Breaking these atoms releases an enormous, steady flow of intense heat, which is used to boil water, spin turbines, and generate electricity. This method gives us a massive environmental benefit. Splitting atoms produces zero carbon emissions. However, it leaves behind hazardous radioactive waste, which has to be carefully stored and managed for thousands of years. While a nuclear plant gives the grid a completely reliable pulse, it is like a massive cargo ship. It takes a long time to start up and slow down, so it lacks the flexibility to quickly react to sudden morning and evening demand spikes. To catch those sudden peaks and fill the gaps when the wind dies down, we use a system called pumped hydro storage. It allows us to move energy across the day, saving surplus power for the exact moment it is needed most. This animated cross-section shows exactly how it works. On a sunny, windy afternoon, when solar panels and turbines generate more electricity than we can use, operators take that extra power and use it to push water up a massive pipe inside a mountain, from a lower lake into a high-altitude reservoir. By lifting thousands of tons of water up the mountain, that excess solar and wind power has been successfully stored as gravitational potential energy, waiting in the form of elevated water. Then at 6 p.m., when the sun sets and everyone turns on their ovens, the operators simply open the valves. The water rushes back down the mountain, spinning turbines as it falls, and instantly delivering that stored midday energy to the evening grid. Giant grid-scale battery parks do the exact same job using chemistry. They act like massive sponges, soaking up the afternoon sun and squeezing that power back out to our televisions after dark. By catching surplus power and holding it in reserve, energy storage smooths out the rough edges of nature, translating unpredictable weather into on-demand human power. Keeping a country running requires operators to constantly juggle these tools, checking the weather, adjusting steady nuclear plants, and releasing mountain reservoirs to ensure everything stays in perfect balance. Let's review how the pieces fit together. First, we have to move power efficiently. Step-up transformers increase voltage and lower current, which prevents the electricity from burning away as heat during its journey. To generate that power, we use renewable sources, which are intermittent and depend entirely on the weather. We balance them with nuclear power, which relies on atomic fission to provide a steady supply, though it leaves behind radioactive waste. Finally, to handle the mismatch between nature's supply and our daily demand, we rely on pumped hydro to store excess electricity as gravitational potential energy. All of this infrastructure, all of this physics, exists for a single purpose. Flipping that switch sends a command through millions of miles of wire, forcing power stations across the country to shift their weight and maintain the balance, all to keep your single light glowing.